We're going to start out with this clean slate. Ferrite core wrapped 20 times with enamel-coated copper wire. With the ends scratched off so that they conduct. None of this wire is enamel-coated, so none of this wire conducts here and doesn't start conducting until you reach the part that I stripped off, which is right at the bottom. All right. Let's see what we can do with that. So now I have a CD4106 oscillator with a 1K resistor going from output to input and a 10 nanofarad capacitor going to ground, and it is producing a sine or a square wave that is going at about 86 kilohertz. If I can stabilize it a little bit. There we go. 90-ish kilohertz. That seems to be working. So now, if I take the output of that going through this little white wire through a capacitor, that is going to make it go around the 0 volt line. And so the next step is to try to see what we could do with that. So this this square wave that I have running at 100 kilohertz, rock stable, and it's coming from the CD4106 inverting Schmidt trigger as the oscillator, and it's going through a very small capacitor, and that's what I'm reading on channel 1 of the oscilloscope. So now I have this ferrite core with 20 windings of enameled copper wire, and I have this wire which is coming from that oscillator, and one side of this oscillator is going to ground and the other side is going through this black wire to channel 2 of the oscilloscope, which right now is reading 0. Now if I take this wire and I feed it through the center of this ferrite core and I connect it to ground, all of a sudden you have a voltage reading. The initial signal disappears because it's going to ground, but now on channel 2 I have an AC signal that's centered around the 0 volt line, and it's 2.26 volts. So now what I'm going to do is I'm going to take the oscilloscope and I'm going to move it over here, and from there I'm going to take a diode to get rid of the negative voltage, and I'm going to put it to connect it right here to go to channel 2. And now you can see channel 2 is a relatively steady wave with a maximum voltage of 1.35 volts. And 1.35 volts, and it's almost DC. So now let's see how we can use that voltage output to generate some kind of a signal that we can use. So now I have this TLO 74 op amp, which is 4 op amps in one, and it's wired to positive 5 volts and ground. And I have here 100K potentiometer wired as a voltage divider, and so the center pin is going to channel 2 of the oscilloscope, and right now it's the blue tracing. It's reading 2.92 volts, and as let me zoom out, and as I turn this clockwise, it can go all the way up to 5 volts, and counterclockwise goes all the way to 0 volts. So that's going to be our reference voltage right now. I'm going to set it in the middle somewhere, 2.5 volts, and we'll go from there. So now we have this TLO74 op amp configured as a comparator, and I have the reference voltage going through the blue wire into the inverting input of one of the op amps. We have the original circuit that was producing a voltage of 1.25 volts in coming out of this toroid, the ferrite core, and that's going to the non-inverting input, and then the output is going through this resistor into an LED, and I have the oscilloscope measuring the reference voltage. So we know it's putting out 1.25 volts, and right now I have the reference voltage at 4.6. So let me lower it down until the op amp can sense until that input voltage is higher. Let me go down, there it is, and I put it down even further. And there we go. All right, now we're functional. So I have the oscilloscope probe measuring the voltage going to the going out of the ferrite core, and it's 1.29 volts, and the op amp is sensing it now. So if I unplug this, no current will flow through the center of the ferrite core, causing no induction of current in the copper wire, and there should be nothing, and the op amp goes off. So that is perfect. So now anything that's going through the core is going to be on, and anything that's coming from around the core is not going to be going on. So if I took this wire out from within the core, and let's try to do that without disrupting everything, and let's say I put it near the core, the op amp does not go on. If I put this close to it, or do any tricks with it, like try to bring a loop of it through there, nothing happens. It doesn't go on. The only way it will go on is if it goes through the center of the core. I'm doing this with one hand, it's fun. And if I plug this into ground now, the op amp goes on. So now we have to find a way to control all this. So now I have the signal that comes out of the oscillator and capacitor going to the collector of a 2N2222 NPN transistor. The base of that transistor is connected through a 100K resistor to this wire right here. And the collector, or the emitter rather, is going through the center of the core. And so now we should be able to control this by turning off or on the resistor. So if the resistor goes on, by plugging this into 5 volts, then it reads. If it's on ground, it does not read. The transistor does not conduct. So, in this way, I could turn the whole circuit off and on just with this transistor. So, using all these analog components, I basically have the 1 bit of information that's stored in that ferrite core, and this functions as an address line. And if I turn on the address line, the data, which is 1 at that core, gets transmitted. And when it's on ground, the address line is off, it does not get transmitted. So let's extrapolate this and increase the scale here. Now I have 4 bits worth on a single address line. As you can see, the wires passing through all 4 cores. And I have 4 separate comparators. And I'm going to do it one address line, and let's see if I turn this to power, all 4 lights go on. Fairly well controllable. So one address line. Works beautifully. And all 4 comparators on the op amp are working. So that's 4 bits in one address line. Now we have skipping first one and the third one. So it should be 0101. And let's see if I turn the address line on. It is 0101. Alright. We have a working ROM. And it's all about how this goes. Now each subsequent address line is going to go and make its own bit pattern. And we'll make an 8-bit one. I set up a separate NPN transistor driver for a second wire. This one is a black wire right here that's going through the opposite 2 cores. And so you can see that it's giving you the 0101 version, read from right to left. As opposed, and I turn it off the standard way, power it, go on and off. And if I put both of them on, both address lines on, which we're not going to do in the future, but just for now, the other 2 should come on. There they go. So, now if we turn them both off, it doesn't display anything. So, 2 address lines, address line 1, address line 2, each requiring its own individual transistor. And the input of that transistor is that same oscillator circuit that's going through that tiny capacitor there. So now, using another one of the Schmidt trigger inverters here, I set up a low frequency oscillator with a 470k resistor and a 10 microfarad capacitor. And you can see it blinking away here. That's the timer, or that's the clocking. And that, the output of that, in addition to going to the LED, is going to this CD4017 counter, my favorite chip. And what it's doing is counting between 0, 1, and then resetting on 2. And then what that is doing is the 0 and the 1 outputs are going to this transistor and this transistor, and to cycle through the 2 address lines that I made. And you can see the result. And so each address line has its own data. It's 4 bits of data. And it's going between 5 and 10 in binary. So, as you can imagine, this could be scaled up much further, and as many address lines as can fit through the center of these toroid coils can be made to make this core rope memory. So now I have this circuit cycling away at with 4 address lines now, And you can see each address line has its own pattern, and it's being cycled by the CD4017 counter. And there's 4 different lines going through and outside of the 4 toroid or ferrite cores. And it's basically each line going through them is an address line. And so this is hardwired in there, and it's equivalent to read-only memory. Not only that, but it is actually it's a ROM. It's the read-only memory that was used, in fact, on the Apollo space mission guidance system. So this is a tribute, and I'm paying homage to the old school technology here, using as little digital stuff as possible, just op amps, transistors, and ferrite cores. So thanks for watching.